Now, question number 4. So for question number 4, we'll attempt two problems. I will do question number 1.2 and the last question here, which is a quadratic sequence problem. So let me rewrite question number 1.2 if it's not clearly visible. We are required to find the value m, and we are given, okay, we are told that the sum of 3r minus 1, where r is equals to 5, to m, minus the sum of 2 to the power 7 minus p, where p is equals to 1 to infinity. The difference of these two sums gives us 1. So the question states that calculate the value of m. So we're required to find what this upper bound is. In other words, when we are computing the sum of this nth term, at what index do we end? That's the question here. We need to find what m is. So for both sums, before we can begin, we need to at least determine our first term and then our ratio or common difference that is depending on the nth term. So for this one, since we are adding to infinity, I'm expecting that this is a geometric sequence, right? So that means we need to know what the ratio is. And once we have these two, we can now find the sum to infinity using the formula 1 minus r, where r is not equals to 1. So we'll first simplify the sum because in this case, we do not have a variable m. So I'm expecting us to get a whole number. And once we have the sum of these, we'll transpose the sum to the other side. And then we equate the sum of this sum to our value. And then we solve for m. But first, let us determine what our a is. To do that, we'll just write the first three terms of this nth term. And we'll substitute our p is equals to 1, 2, and 3, right? So when p is 1, that means we'll have 7 minus 1, which is 6. So 2 to the power 6, we've got 64. And then when p is equals to 2, 7 minus 2, that's a 5. 2 to the power 5, that's a 32. And then 2 to the power 4, that's a 16. Okay, that's enough to determine our ratio. So our first term is given by 64. And then the ratio, I will say T2 divided by term 1 should be consistent with term 3 divided by term 2. So I will use this one and this one, term 2 and term 1. 32 divided by 64, and that is just a half. So this is our ratio for this geometric series. And now I have my a, I have the value r. We can now compute the sum to infinity. So our a is equals to 64, 1 minus a half, 64 divided by, that's going to be a half. So the sum should be, that's 128. So that means now our equation, we've got the value 128 here. And I can transpose this negative 128 to the other side so that I have, I'll have this sum is equals to 1 plus 128. Okay, let me rewrite this in a new space so that it's much neater. So Let's move this. So now the new equation, I've got the sum of 3r minus 1, where r is equals to 5 to m, is equals to 1 plus 128. That's 129. And then again, let us write down at least the first three terms of this nth term, and we'll substitute our r is equals to 5, 6, and 7. So when r is equals to 5, 3 into 5, that's 15 minus 1, that gives us 14. And then 3 into 6, that's 18 minus 1, 17. And then 3 into 7, that's 21 minus 1, that's a 20. Then up until some value 3m minus 1. So now our first term is equals to 14, and then our common difference, because notice that this is a linear pattern, so the common difference there is 3. And now once I have that, I can now use my formula to find the sum of linear sequences, which is given by n divided by 2, then 2a plus n minus 1 multiplied by the common difference. Or you can use the sum where we have n divided by 2, and then you add the first and the last term. So for this case, I will choose the long one, right? Just because since this is the one that we mostly use. But even if you use this one, where your L is the last term, which is this term, you should arrive at the same conclusion when we use this one. Oh, and another thing that I'm missing, we don't know what our N is. We do have our A, we have our D. Our only unknown is N. And the N is not this value in our sigma. It's not the upper value. Our total number of terms, which is N, is given by the upper bound minus the lower bound plus 1. So our upper bound in this sum, it's m. So that's going to be m minus the lower bound, which is 5, then plus 1. Therefore, our n is equals to m minus 4. So now we have our n, we have our first term, we have our common difference. We can now compute the sum of these nth term. So m is given by m minus 4 divided by 2 multiplied into, what is 2a? 2 times 14 will get 28, right? So I'm just substituting. Not substituting, I'm multiplying. So but you can first do your substitution and then you do the multiplication. I'm just constrained by time here. So our n, it's m minus 4. I will therefore have m minus 5, since I've got a minus 1 there. And then all of that multiplied by my common difference, which is 3. Now let me simplify inside my brackets. I will have a 3m and minus 15. So 28 minus 15, that's a positive 13. Okay, and this is our sum of n terms. So now remember what we have up there, our new equation, right? We had this. So now I can rewrite this and say I've got m. Okay, let me zoom in here. we have m minus 4 and then 3m plus 13, right? So we have a divide by 2 there, and this is equals to that value 129. Why am I saying 128? That's 129. Yeah, and we only have one variable, so we can solve for m here. So to get rid of this denominator, I will multiply both sides by 2. So I will have 129 times 2, which is equals to 258. So I can just say this is 258. And this is not the final answer. Don't make the mistake of just saying m minus 4 is equals to that, because you are going to get the incorrect value of m. We need to expand this, and then we equate this to 0, and then we simplify, and then we factorize and find our value of m. So expanding the left hand side, I will have 3m squared plus 13m. Then I will have minus 12m. Then what is 4 times 13? That's a negative 52. Then I will transpose this to the left. I'll have minus 258 equals to 0. Then my like terms, I will have 3m squared plus m, then minus 52 minus 258. That gives me negative 310 equals to 0. Now I need to factorize this. Yeah, and for factors of 310, I'll just use my quadratic formula to find what my values of m are. Okay, my values of m, I'm getting m minus 10 and 3m plus 31. So that means we've got m is equals to 10, or we have m is equals to a negative 31 divided by 3. And our valid solution of m is equals to a 10. And you can double check that. Let's go back to our original problem. We know that this sum is 128, right? So obviously to find your answer is 1, we need to have at least another sum that is one more value. So in other words, this is expected to be 129 minus 128. So you can just double check whether really your m is 10. And then you can just use, let's see, you can just use this formula. And remember that initially your n was m minus 4. So instead of this, you can substitute, what is our m? Our m is 10. So for n, you can substitute n is equals to a 6. And when you substitute n is equals to a 6, you should at least find the sum as 129. And now let's go to question number 2, which is a geometric, not a geometric, a quadratic. So I'll just read this out loud in case you can. So question 2.1. I'm told that 4x, y, and negative 11 is a quadratic sequence, right? So this is a quadratic sequence. And then we are told that 2p minus 4 and p minus 3 and half p minus 1 are the first three terms of the first difference of the quadratic sequence. Calculate the value of p, x, and y. Okay, so what we can do, we can first work with this the second part of the information, right, where we are told that the first three terms of the first difference of a quadratic sequence, which is this part, and why this part. So one thing we know about the first difference of a quadratic number pattern, it's that it forms a linear sequence. So using these terms, I know that these terms form a linear sequence, and therefore I can construct an equation and say term number 2 minus term number 1 is equals to term number 3 minus term number 1, because the difference is consistent, because this is a linear number pattern. And so what is my term 2? That is p minus 3. I will therefore substitute p minus 3 minus term number 1, which is 2p minus 4. And this is equals to our term number 3, which is half p minus 1 minus, okay, I made a mistake. I was supposed to say t2 minus t3 minus t2. So I don't know what happened. So term 2, term 3 minus term 2. And term 2 is p minus 3. So let me get rid of my brackets and then simplify my like terms, and thereafter I will need to solve for p. And also notice that this is a homogeneous equation because there's only one unknown, so which makes it possible to solve for p. So therefore here I will have minus p and plus 3. What is positive half minus 1? That's going to be a negative half p, and then I will have a positive 2. And then let's simplify this side. We'll have p minus 2p, which is a negative p, and then minus 3 plus 4, which is a positive 1. And then I can resolve my like terms, right? I can say, let's just say minus p plus half p, and then we'll have 2 minus 1, which is just 1. And that means here we'll have negative half p minus half p is equals to 1, and then we can multiply everything by negative 2. Therefore our value of p is equals to negative 2. So now we've solved for p. We know that p is minus 2, so that means we can rewrite these number patterns. We can say 2 into minus, that's going to be minus 4 minus 4. That means we've got negative 8, and then minus 2 minus 3, that's a negative 5, and then negative 2 times half, that's a negative 1, minus 1, that's a negative 2. And you can even double check whether really the common difference in these terms is consistent. However, I will not do that, but the difference is just the positive 3. You can double check that on your own. So really, the first three terms of the first difference of these quadratic number pattern is given by negative 8, negative 5, and negative 2, right? And now we can work backwards and say, let me move this. So that means our terms, we still have we have 4 and x, we've got y, and then in negative 11. So that means the difference between 4 and x, we've got minus 8. Okay. And then the difference between x and y is minus 5. But then for now, that doesn't matter. So I can find my second difference, which is just positive 3. And in order to solve for what x and y is, I will just determine the nth term of this equation. So we know that this is a quadratic number pattern. So I'll just try and find. So and we've got enough information to determine our a, b, and c. So we'll just say 2a is equals to that, and then a plus b. No man, that's 3a plus b is equals to that, and then we have a plus b plus c. So a is equals to 3 halves, and then for our b is equals to minus 8, then minus, that's going to be 9 divided by 2, so minus 9 divided by 2. I don't like these fractions. Let me see what my b is. Minus 8 minus 8 minus 9 divided by 2. So our b is negative 25 divided by 2. And then our c, that's 4. So I've just transposed everything to the other side just to save space here. So I have minus a minus b. So minus 3 halves. Then this will be plus 25 divided by 2. So my c, 4 minus 3 halves. Then minus, oh, that's plus 25 divided by 2. So c, it's 15. Therefore, the general nth term of this sequence, it's defined by 3 halves n squared plus, what is b? Okay, that's not plus, that's minus. Minus 25 divided by 2n plus 15. And to find what our x is, notice that this is at index 2. So we need to find what our t sub of 2 is. And we can substitute n is equals to 2. And then similarly for y. So this is for x, and then this is for y. So for y, we are at index 3. So t sub 3. So I will just do my substitution. That's 3 halves into 2 square minus 25 divided by 2 into 2 and plus 15. So x is equals to a negative 4. And then let me see what y is. Y is a negative 9. So therefore, our sequence is 4, negative 4, negative 9, and negative 11. And then you can just double check. We've got minus 8, minus 5, minus 2. So yeah, this does look correct. So that's how you solve for x and y.